I'd like to invite our next speaker, Sethu Vijayakumar, from the School of Informatics at Edinburgh University. I think this is a bit of a double act, so it's going to be quite interesting. So Vijay's at Edinburgh University. He's worked for a long time in pioneering research on large-scale machine learning techniques for real control of high degrees of freedom, anthropomorphic robotic systems. I can't pronounce the word, as actually you already know. He's basically is also is a member, fellow of the Royal Society of Edinburgh. And I'd like to invite you onto the stage. Thank you. Thank you.
Thank you all for the invitation. It's a great honor and privilege to be at the Royal Society, and it's also a great pleasure to be with lots of old friends. So I'm going to talk today about shared autonomy in robots, essentially shared control with robots. And that's a topical thing that's really raging at the moment about how autonomous should our robots be, how much can we actually devolve control in various systems, everything from prosthetic systems to autonomous driving cars. So really, if you look at the spectrum of robotics, the traditional robotics, it goes all the way from teleoperation to things like full autonomy. And this is what David mentioned early about the DARPA Robotics Challenge, where the challenge was really ask the robot, give it some sort of really high-level tasks to say, this is a start position, you need to open a door and get through something and then actually turn a valve. And obviously the challenge was to push the autonomy boundary as much as possible towards the right. But my honest opinion is that the real challenge and the real sort of innovation is going to come from somewhere in between, which I call shared autonomy, where really the idea is you want to push the envelope of autonomy as much as possible, but have the ability to scale it back and be adaptive at that level of autonomous behavior. So actually, this is not just restricted to the domain of humanoid robotics. If you look at the various domains that we can see in robots make a difference in today's society already, all the way from prosthetics to self-driving cars to things like the Baxter robot. There are lots of challenges in robots that interact. So these are domains where robots interact, and getting full autonomy has got significant challenges because of problems like what I've listed here. So I'm not going to read it out. So noisy sensing, dynamics, most importantly, unmodeled user intentions. So how do we get that into the picture? So how do you get people into the picture and do control by closing the loop there? So this is not completely a new idea. More recently, there's been a book out by David Mindell. I mean, I'm not sure everybody necessarily buys into this idea, but I found some of the interesting quotes from there, which says things like, full autonomy is a 20th century rhetoric because the real frontier is a collaboration where the different levels of autonomy at different moments at the control of a human operator. So again, such systems should have the ability to turn on autonomy when it can be helpful, and with the ultimate aim of reducing human workload and fatigue while still keeping human in the loop. So hopefully, somewhere in the middle of my talk, I'll get to show you a live demonstration of some of this concept of shared autonomy. So now, going back to this list of problems or the list of things that we need to deal with when we have robots that interact. So what I want to do is to spend the next 10 minutes or so trying to look at key underlying technologies that we've been developing, the community has been developing in trying to overcome some of these great challenges. So there are three things that I want to focus on. One is about sensing and representing the world around you. The second is about having safe interactions, so robots that interact safely. And the third bit is to do with learning and prediction and adaptation, and this is what Andrew just talked about. So let's start with understanding and representing the world around you. So here's a little quick video of some work that's come out of our lab on real-time object pose tracking and recognition under quite severe conditions of occlusion, object and hand occlusion, and eventually you will see it's out of the camera, the range of the depth camera, and you'll have external occlusions of the objects that you're trying to track, and eventually, this is visual servoing, for example, under these rather severe conditions, but also you will see in a moment that as with all autonomous robots, you will not have cameras that are on fixed basis. The camera themselves move. So you will need to able to do this kind of robust tracking and calibration under circumstances where the camera themselves move. So in a moment you will see the same sort of visual servoing happening with the motion of the camera in the picture. So this again, the underlying technology behind making that happen is to do with things like using machine learning and data-driven techniques to understand what it takes to do robust tracking under occlusion, under motion, under, say, in this case, a very cluttered environment. So, and where can this possibly be relevant? So this can be relevant in scenarios like, in this case, an example is the Toyota's human support robot system, where the idea is you want a robot be really a co-helper, in this case, of a feeding scenario. So, and it's not enough if you just create a raw percept tracking on its own, but you really need to create a unified percept of the world around you. In other words, really interpreting the scene around you. And one example of that work that we've been working in collaboration with the MIT DRC team is on taking raw sensor data, things like LiDARs and depth sensors and camera sensors, and really mapping the world and doing control on top of it. So the next video that you'll see is really applying this technology to a control of a fully autonomous humanoid robot. And as you probably all recognize, is the Atlas. And the idea is you want to be able to, in this case, locally track the world around you, be able to figure out what are the footsteps and feed it back in real time in terms of the planning, the feedback control, and all with this kind of rather impoverished view of the world. So this is a big challenge, and we are seeing solutions. I'm not saying this works in all circumstances, but we are getting to a stage where we are able to map complex scenes, plan ahead, apply all these machine learning techniques that we've been hearing about to actually achieve this closed loop behavior. So in this case, it can be simple things, steps like baby steps, literally, like figuring out the three-step look-ahead plan, taking terrain segmentation from sensing, using some good clustering algorithm, and doing some clustering, segmentation, and in the end, footstep placement for navigation. So this is where we really want to push the boundary of sensing all the way to actual control in the loop kind of scenarios. The other bit that is important to understand and represent the world around you is to talk the same language. So sensors have a certain kind of language, pixels, depth maps. You and me communicate in very different ways. We communicate using things like, I want to put this on the top of the table, or I want to put this under the object, things like that. So how do you bridge this representation? And one of the keys to doing that is looking at representations that actually capture the essence of what it means to do a particular task. And I won't go into all the details, but we work with things like interaction mesh-based relational descriptors. I'll show you a quick video of how that illustrates that point. So here's an example of asking a robot arm to reach inside a box. Okay, you can specify it using X, Y, and Z. But the point is, if you use relational descriptors and topology-based descriptors, then the concept of what is inside and outside a box moves with the box. And hence, you can actually very quickly readapt and change the behavior of an object that you're trying to track without explicitly encoding collision avoidance. So as long as the hand is inside the box, it doesn't care that it's in the center of the box, because that's not the specification. So here's an example of how you can use interesting representations to do clever, fast things. Now, in spite of good representations, you will always have the situation, Andrew mentioned uncertainty, probabilistic inference, you will have uncertainty in the world, and that's the nature of the world, that's the nature of the real world. So to be able to deal with uncertainty, one of the many approaches that we have taken is to look at actuation systems, fundamental actuation systems, and work with compliant actuation systems. So in layman terms, it's springs in between your motor and your end effector. That's great. The problem is controlling such things. So the moment you put those things, controlling them become really, really hard. So we've been developing algorithms that are able to do that. So combined with efficient representations, we've been looking at algorithms which are able to do good level of optimal control with compliant actuation systems. So why is this important? So why is compliant actuation important? David had an example early on about manipulating a valve underwater. Great example. If you're not compliant, then you probably won't succeed. Something closer to what I do, we do work with a lot of exoskeleton systems. So things for supporting a human body, for augmenting power, for rehabilitation purposes. So this is an example of a exoskeleton from Cyberdyne in Japan, and it should not have a mind of its own. So you need a system which really works with you. So if you take that idea, and I want to show you a little video which combines the concept that I showed you about representations, so clever representations, and human-in-the-loop compliant actuation. So this is a Baxter robot, and here we have tasked it to have a primary task. So this is compliant actuation here. So it is able to adapt to human in the loop. But you will also see that while a person is trying to interact with it, it is able to adapt its motion while, in this case, still maintaining the primary goal, more or less, of keeping the bottle above the glass. So this is an example of how we can get real-time human interaction in the loop while compliant actuation is aiding us to have this safety net in the picture. So this is not just a picture that I just put up. That's me wearing one of those exoskeletons. So if things don't work, my health is at risk. So we do a real patient and trials with human patients on using these exoskeletons. And this is actually an active pelvis orthosis. Last bit of the technology that I want to focus on is something close to what Andrew talked about, which is about the key ability of people to predict consequences and task goals and intentions. So we need systems that are able to adapt and change to novel situations, novel circumstances. And here's a little example, and this is actually research that's quite old. This is from the time of my PhD. But this is about a robot arm doing what we call motor babbling and learning from these examples the ability to essentially doing the mapping between the force that's being applied and the consequence of an action. So this is just like a baby does discovers the sensory motor behavior. It's a way of getting a machine to learn this. And what can you do with that? You can now, on top of that, build something like learning task dynamics. In this case, it is a rather playful task of trying to balance a pole. It's quite hard to program this because otherwise you would have to put a program for different weights and different lengths of the pole. But if you use a data-driven approach, you're able to use the data to tell the value of every action and use that to actually, in the end, get a robot to balance a pole without actually pre-programming everything. Okay, so this is a toy example. We are now scaling this up on a much bigger scale, thanks to EPSRC for a grant that's been funded called on the Any Scale application. And the whole idea behind this learning framework is to take this and plug it in within a stochastic optimal control framework, do this, but not just do this for low dimensional systems, but do this for high dimensional, high degree of freedom systems, where you can do this at scale. Depends on the scale that you care about, embedded, cloud, or tethered systems. So that's the vision about taking this adaptation over. Okay, so now comes the fun part. So what I want to do is to show you two pieces of work that use the technology that we've just talked about and illustrate this concept of what is called shared autonomy. What do I really mean by shared autonomy? So can I ask my good friend Nick Roy to come up and help me with this demonstration? So what Nick is wearing is actually a prosthetic hand. So maybe Nick, is maybe a better idea to go up here. So thank you. And so this is a prosthetic hand. This is an iLimb prosthetic hand that is being developed in collaboration with an SME. And this is actually a product that real patients use. And what I'm going to try and do, and these are EMG sensors that sense the muscle activity on my hand. So if I get this right, if I get the polarity right, I think we'll hopefully so live demos are always scary, but
for whom?
Good question. Okay, so polarity is not right. Okay. Try again. Okay, so now what I'm able to do is using my EMG sensors, being able to control in real time the grasp on this prosthetic hand. So it is giving open and closed signals from my hand, and a lot of the smarts are in the hand. So, for example, what we can try and do is to grasp various objects. So, in this case, a ball, which is a rather hard object, an object of not very systematic shape. You could grasp something with a heavy load, and this is a bottle filled with water. And you can see it pulsing and almost brilliant. But where is the shared autonomy here? So, Nick, if I can get you to hold this. So what I can do is I can turn away from what Nick is doing, and if you put the ball against it, and I can not necessarily.
I missed
Oh,
it, sorry.
you okay? Okay. So I can turn away and not look at what's happening, and then release the ball. I'm going to release the ball, Nick. Okay, so basically the volition is coming from me, but a lot of the smarts are built into the hand, and that's where the sort of taking away this cognitive load. I could create a robot that mimics every hand movement and use my actual thought to control individual fingers, but that would increase the cognitive load on the person, and that is really not what patients need on this. So thanks a lot, Nick, for that. Great. Thank you. Oh, it's okay. So I waited a long time to say this, that I'm controlling the right hand of Nick Roy, the ex-director of Google X, since the time Google bought Boston Dynamics, you see. So here's my... So that is an interesting example of sharing autonomy. So the last bit I want to finish with, oh yeah, I'm going to skip this. The last bit I'm going to finish with is to show you a little bit on the DRC and the SRC. So again, just a little note that this is an example of a successful partnership between a rather small company, an SME called Touch Bionics, just off Livingston, and the University of Edinburgh. So it's a good example of where things go right. So, as probably most of you know, there was the DARPA Robotics Challenge, the autonomous driving cars. A lot of the success has been attributed to the first challenge that DARPA did. Now, they had a similar thing on the humanoids robot. The challenge was to drive a vehicle, dismount, do some tasks, and climb a ladder. So it was exciting. But the reality was that a lot of the robots did reasonably well, but there was a whole team of people underneath the hood doing really more or less teleoperation. So the idea is, how can we push the autonomy slider a bit more so that we still have human in the loop, but do this quite a lot more autonomously, a lot more robustly. So towards that, one of the programs that we are driving now is on going to the next competition, the next level of competition, using a flagship Robotarium platform. Robotarium, by the way, is the equipment platform that we have at Edinburgh. It's a collaboration between NASA and, again, this is a good example of a case where UK research, the academia, is coming together to try and attack a bigger problem. So the UK Hub of Humanoid Research and Space Robotics Challenge, especially we had a first sandpit using with multiple universities, King's College, Imperial Labs, Birmingham, and so this is an open call for everybody else to participate. So what was this challenge about? So the NASA challenge is about getting unmanned unmanned missions at much cheaper cost. So they have this vision of robots doing things like spacewalks, and somebody said, Rob Ambrose said actually, if Columbus had the vision, he would have sent a person ahead to set up his landing team. The only problem is he would have had to answer the question, where is America and what is a map? Anyway, so last slide, this work that I've just talked about, mostly focusing on motion synthesis for robots in contact-rich environment, has just this one topic, has a capability to interact or create interactions across domains with academic partners, with industrial partners, with companies small and large. So this is just one example of a successful partnership that's happening between universities and, in this case, my research team. But there are lots of examples out there. So this is just a call to say that we should work closer and with much more. We would do much more if we are able to do that. So again, a plug for the Edinburgh Centre for Robotics. So if you want to play with some of the toys that I showed you here, and any of you are interested in doing some research with us, please come talk to us, me or David. We have some exciting platforms and exciting places to do things with. Finally, I would like to end with this quote. We tend to overestimate technology in the short term and underestimate technology in the long term. So that is indeed the case. So we need a vision to think about where things are going, but at the same time, we need to give people the slack to show results and not think about short-term goals. Thank you very much.
Thank you very much, Sethu. We've got probably time for 2 or 3 questions. Actually, any questions from the floor? Can I also remind people to use the online question system as well? Are there any questions? Can I just ask you a question? Actually, a lot of what we've seen here obviously interacts with humans.
Yep.
And there's been a number of questions that's come up actually on the website of things actually about the safety critical nature of these validations, verification. Obviously, I come from an aerospace background, which is that's bread and butter to us, and it's also a limitation. Can you comment actually on approaches for that actually within this domain?
Yes, so a lot of the underlying technology, which I didn't talk about in detail today, on stochastic optimal control, the adaptive control, all of this thing, we still, under the hood, we still worry about Lyapunov stability, convergence, things like funnels for limit cycles. There are cases where that doesn't work. There are cases where we have to take it out of our comfort zone, but the underlying base that we start with indeed does worry about these problems, both from a theoretical and analytical point of view, as well as when we generalize to some things that can't be captured, we have a certain set of tests that we actually run through. So this is paramount. So we start by looking at classical techniques, but we have both data-driven as well as test-based methods for ensuring safety.
Are there any other questions? I think there's just one down here, please.
So to contrast your talk against Andrew's talk, it seemed, to contrast your talk against Andrew's talk, Andrew made the point that an awful lot of data can be required, and so it might be nice to have more symbolic models under the hood. And I'm curious to hear whether or not you can do the same, or is there enough variability across people that you actually have to relearn from person to person?
Yeah, so that's a good point. So the variability across people. So we call that the null space of the human motion. So there are cases where you can capture the essence of a movement and still allow variability, and that is very relevant in a domain like the prosthetics domain. So we see some very good examples of this. There's a company called Hokuma in Switzerland which developed the CyberLegs thing. So this is actually a rehabilitation device. So the original idea was you take a standard template of a person walking and try to fit all patients and get them to walk in that way. It works okay for getting some core capabilities back, but the moment you realize that every person walks slightly differently, then the real aim has to be, how do we tease out the common part of the walk, and how do we still allow for natural variations in the systems? And there are techniques, and again machine learning techniques, to be able to tease out what is called the null space movement and the underlying task space in the movement. And if we are able to do that, then we can apply that to these kind of shared technologies. And this goes all the way across spectrum for human-robot interaction, collaborations, etc.
Thank you. Any other questions? Can we thank Sethu for a very interesting talk?